Hey there, ready to dive into something really cool? We're tackling this whole gamma ray excess mystery coming from the center of our galaxy. Yeah, it's been puzzling scientists, and we're going to see if this Coy dark matter thing might be the answer. You sent over this paper, Extended Gamma Ray Emission from Coy Dark Matter. Gotta say, the title itself had me hooked.
What's this gamma ray excess all about?
Well, imagine like this faint glow, right? But it's gamma rays, super high energy light, and it's coming from the heart of the Milky Way. That's what the Fermi-LAT satellite's been seeing, and it's got everyone buzzing.
A cosmic mystery, huh?
Yeah. There are a few ideas floating around about what might be causing it, but today we're diving deep into one captivating possibility, dark matter annihilation, just like that paper you sent over suggests.
Right, dark matter. Always a fascinating topic.
It's this big enigma already. We think it makes up a huge chunk of the universe's mass, but it's seriously stealthy. Doesn't interact much with light or regular matter, hence the name dark. But this paper, it takes it even further. It proposes a form of dark matter that's even more elusive.
Even more elusive than regular dark matter. That's hard to imagine.
Exactly. They call it Coy because it interacts just strongly enough to maybe, just maybe, cause this gamma ray excess, but not enough to show up in our attempts to find it directly. Like, try to hear a whisper in a crowded room, you know something's there.
And
But
you can't quite make it out. Okay, I'm definitely intrigued now. So how do they explain this whole Coy dark matter thing?
well, they propose that this dark matter particle, it's a type called a Dirac fermion.
Dirac Fermi.
Now, that might sound a bit intimidating, but just think of it as a specific type of fundamental particle, okay? And to understand how they interact, imagine like a game of cosmic billiards, but with a twist.
Oh, I like where this is going. A cosmic twist.
Right. So you've got these Dirac fermion dark matter particles are billiard balls, and sometimes they bump into each other, right? And when they do, they annihilate, like a collision that releases a burst of energy. That energy in this case would be other particles, including those gamma rays that Fermi-LA might be picking up.
Okay, that makes sense.
But here's the twist they propose, that these dark matter particles, they really prefer to annihilate into a specific type of particle called a bottom quark.
Interesting. Bottom quarks. Why bottom quarks, though? What makes them so special in this whole scenario?
So they're drawn to these bottom quarks, huh? Is it like they're the cool kids in the particle world, or is there something else going on?
It's more about a specific kind of attraction, in the world of particle physics. The paper suggests that this Coy dark matter, the way it interacts, it's governed by something called Yukawa couplings.
Yukawa couplings. Sounds intense.
Yeah, it's a bit of a mouthful.
Yeah.
But think of these couplings like a measure of how strongly particles are attracted to each other. And it turns out that the heavier the particle, generally the stronger the attraction, at least in this model, that is.
So bottom quarks being on the heavier side, they really make those interactions count.
Right. It's like a cosmic dance floor. And those bottom quarks, they really know how to cut a rug with this Coy dark matter.
Love the analogy.
And here's why that's so important. This preference for bottom quarks, it actually lines up with the type of gamma ray signal that Fermi-LAT is seeing, like a clue that points us in the right direction.
Okay, so we've got our mysterious gamma rays, maybe coming from this elusive dark matter, which has a thing for bottom quarks. But, how well does this model actually fit the data? Did they just throw this idea out there, or did they actually, crunch the numbers?
They crunched the numbers. And that's where things get even more interesting. They found that their model, with this Coy dark matter and its specific interactions, can actually reproduce the gamma ray excess we see.
Wow, so it's not just a cool idea. It actually might hold water.
And there's more. The mass range for the dark matter that works best in their model, it's around 20 to 50 GeVs.
Okay, and 20 to 50 GeV, is that significant? Like, why is that range particularly exciting?
Think of it this way. Other experiments, the ones trying to directly detect dark matter, they're also looking in that same mass range. So it's like having two separate telescopes, both pointed at the same intriguing spot in the sky. It doesn't confirm everything, of course, but it's definitely a point in favor of this Coy dark matter idea.
Right, like a little nudge from the universe saying, hey, you might be onto something here.
Exactly.
But hold on, if this Coy dark matter is so good at hiding, wouldn't that make it even harder to find, even if we're looking in the right mass range?
Yeah, that's the challenge. The paper acknowledges that direct detection experiments, the ones looking for those rare instances of dark matter bumping into regular matter, they're unlikely to see anything with this model because the interaction is just too weak.
Too subtle, huh?
Way too subtle, like trying to hear a whisper in the middle of a rock concert, the signal is just going to get drowned out.
So if direct detection is out, what about those other methods, the ones that look for clues rather than the particles themselves? Do those offer any hope of tracking down this elusive stuff?
So it's like trying to find a needle in a haystack, but the needle's invisible, and the haystack is, well, the entire universe. Are there any other ways to pick up on this Coy Dark Matter's signal? What about those indirect searches, the ones looking for the aftermath of these particles?
They thought about that too. They explored indirect searches, the ones that look for things like extra antimatter particles, which could be a byproduct of dark matter annihilation, you see.
Right, looking for the evidence rather than the thing itself.
Exactly. But from their calculations, it seems those methods might not be much help either. It's like this Coy Dark Matter is really committed to staying hidden.
Okay, so our shy little particle is being quite the challenge. If it's too coy for direct detection and hiding from our indirect searches, how are we supposed to know if it's even out there? Do we just have to wait for another cosmic clue like that gamma ray excess?
Not necessarily. There's another possibility. The paper mentions particle colliders. You know, those massive machines that smash particles together at crazy speeds?
Ah, you mean like the Large Hadron Collider, the LHC, the one that found the Higgs boson? That's a whole other level of science.
It is, but that's often where the hunt for these kinds of particles leads us. Now, the LHC hasn't seen any direct evidence of Coy dark matter yet, but the paper suggests that future runs, especially with the upgrades they're planning, they might be able to reach the energy levels needed to actually create and detect these particles. So it's like we're pushing the boundaries of what we can explore, trying to create a glimpse of this Coy dark matter ourselves.
So instead of waiting for the universe to give us a sign, we're building tools to try and make those signs ourselves. That's pretty amazing when you think about it. You've taken what could have been a really dense and complex research paper and made it really understandable and, dare I say, entertaining. So for our listener who's been on this journey with us, what would you say are the key takeaways? What's the headline here?
Well, I think the biggest takeaway is that while this gamma ray excess at the galactic center is still a puzzle, this Coy dark matter research gives us a new way of thinking about it. It reminds us that we might need to rethink our assumptions about how dark matter behaves, and that finding it might require even more creativity and persistence than we thought.
It's like the universe is whispering secrets and we just have to fine-tune our listening skills, right?
Exactly. And you know what I find particularly exciting is that even if this specific Coy dark matter model turns out to be something else entirely, it's opened up new avenues for exploration. It makes you wonder, what other subtle clues might this or any other kind of dark matter be leaving behind, just waiting for us to uncover them?
Now that's a truly fascinating thought to end on. It's like we're setting off on a cosmic treasure hunt with the universe as our guide. This has been a fantastic deep dive, and a huge thank you for walking us through this intricate research. It's clear that the quest to understand dark matter, whether coy or not, is far from over, and I, for one, can't wait to see what amazing discoveries are still out there. Until next time, keep exploring, and as always, thanks for taking this deep dive with us.